Hello, my name is Andrew, and today I'll be explaining the 2012 AP Calculus BC FRQ question 4. Now, before we get started, it's good to identify what the question is asking for. In this case, it's a table question, which shows up on pretty much every AP Calculus exam, so don't be too surprised when you see one. Now, it's good to identify what the table actually says, and it's actually giving us f derivative of x values, not f of x, not f second derivative of x. I once actually made this mistake, and on the test, it'll cost you almost all of the points, or a lot of the points, depending on the question. Now, the second thing you want to do is keep out for units. Now, in this specific question, usually it's in a context question where there's like context. In this question, we don't, but be careful. Now, when you're reading the question, it's good to underline in order to identify the key information. In this case, it says that the function is twice differentiable for x is greater than 0, which suggests that we're going to be using a second derivative to a certain extent. And this is further backed as we get f of 1 equals 15 and f second derivative of 1 is 20. And these both suggest that we're going to be using these values at a certain point. As the College Board likes to only give values that are useful and not redundant. Now, going to part A, we should also underline it. So as you can see, it says to write an equation for the line tangent to the graph of f at x equals 1 and use this to approximate f of 1.4. Now, conceptually, if you have a graph such as f and you're trying to approximate at x equals 1, a tangent line is essentially a linear line that's touching it at one point. And what you're using with this approximation is you're essentially using this line to approximate a point slightly beyond it. So in this case, 1.4. Now this again will have an error, but it is a sort of decent way to approximate it. Now to write an equation, we're using the y equals dy dx, or the slope of x minus the x value plus the y value formula, or the point slope formula. In this case, dy dx can be found on the table at x equals 1, which is 8 on the table. And then we're timesing it by x, which is variable, minus 1, which is what x is equal to in this question. And we're adding it by what y is equal to at x equals 1, which is 15, which is seen above here. Now, from this, this is our tangent line. And on the exam, you'll get 1 point for this. But this is not the entire question, so be careful and read all of the parts. The next part says to use this line to approximate f of 1.4. So in this case, we're just plugging it in. This is essentially what it is for approximating. This is linear approximation, so you're using a linear tangent line to approximate something that isn't exactly at that point. And from this, we get 8 times 0.4 plus 15, and the answer is 18.2. So in the second part of the FRQ, we have a midpoint Riemann sum with two subintervals of equal length and values on the table, using the tables to approximate integral from 1 to 1.4 of the derivative of x, and to use the same approximation for this to estimate the value of f of 1.4. Now you can see a trend here. And in fact, you can notice that all of the parts of this FRQ are actually achieving the same goal, which is to estimate f of 1.4, but using different approximation techniques. This is just something that it's good to know. So for the first part, it says to use a midpoint Riemann sum. Now, again, imagine that you have a function f, which is this is the graph, and it's going from the lower bound, which is 1, x equals 1, to the upper bound, which is x equals 1.4. Now, the integral asks you to find the area under the curve of the derivative graph, but it's unimportant or redundant what the graph is. We just need to estimate using midpoint Riemann sums. And the way you do this is, if it says to split into a certain amount of subintervals, you're essentially splitting this, which is 0.4 in width, into two equivalent ones as specified in the question. And in this case, this would be x equals 1.2. And so on each side, you have like an equal width thing, but now you need to find the rectangle. And in order to find the rectangle, you also need to know the height, not just the width. And you can do this by finding, this is why it's called the midpoint Riemann sum, because you're essentially basing the height and the approximation off the midpoint of this rectangle. So if the first rectangle goes from 1 to 1.2, the step size, or the delta x, is 0.2. And it should be the same for the other one if it says equal values in length. Although this is not always true, and there has been table questions in the past that don't do this. So in this case, the step size is 0.2, so if you divide that by the 2, you find the midpoint, which is x equals 1.1. And when it's at 1.1, we can use the table to find the y value, which is 10. So the height is 10, and the width is 0.2. So this is 1.1, comma 10, and that's the point, and this is a rectangle. Now we can do the same thing for the other rectangle. So the thing between 1.2 and 1.4 is 1.3. So that's the midpoint x value, and then we can use that to find the y value, which is 13, and thus have another rectangle, which is 1.3, comma 13, and that's the second point, or the height. Now, using this, we can approximate the integral. And another tip that I have in doing this is that you should write out the question and what you're setting it equal to or approximating. So in this case, we're approximating the integral from 1 to 1.4 f derivative of x dx. And you should use the wavy squiggly equal signs to show that's approximation. So in this case, integral from 1 to 1.4 and so on and so forth is equal to the area of these two rectangles as its approximation. So we know that the step size or the width is 0.2 and the height is the y value of the midpoint, which is in this case for this one 10. And then you add it by the area of the other one. So again, same step size times by the height of the midpoint, which is 13. Now from this, we can sort of approximate what it is. So in our case for our FRQ, we have a approximate value of 4.6. And that's the first part, but we're not done again. So it's important to make sure you're answering all parts of the FRQ. So the second part is to approximate this. Use the approximation for the integral to find the value of f of 1.4. And this leads into the fundamental theorem of calculus, which essentially connects derivatives and integrals together through one of its theorems, which states that the integral from a to b of a function dx equals to the antiderivative at the upper bound minus the antiderivative at the lower bound. Now this is great because we can apply in approximating this value. So using our approximation of integral 1 to 1.4 of f derivative of x dx, and then we can, the antiderivative of f prime of x is just f of x, as the derivative of f of x is f prime of x. And from this, we can use the upper bound, which is 1.4, minus the lower bound, which is 1. And in this case, we're trying to find f of 1.4, but we know what the values of the integral and f of 1 are. So we can move this over here, and so we got our answer in the first part is 4.6. So 4.6 plus f of 1, which is 15 as specified in the question, equals to 19.6. And this equals to f of 1.4. So for part C, it says to use Euler's method and not Euler's method, but that doesn't count for points anyways. Starting at x equals 1 with two steps of equal size to approximate f of 1 at x equals 1.4. So from this, first of all, we know our step size, or delta x, and this is equal to 0.2. And the reason why we know this is when we're going from 1 to 1.4, this is essentially splitting it into 2. We need to find the midpoint, which is 1.2. So the step size is the distance between this to the midpoint, the endpoints to the midpoint, which is 0.2. Now, using Euler's method is essentially a series of linear approximations designed by Euler to make it more accurate to approximate sort of how a graph looks, so a function looks. So if you have x equals 1 here and x equals 1.4 here, so in part A, we took one linear approximation and we approximated what the y value was when x equals 1.4 on the tangent line right here. The issue was this was slightly far off. Like you can see there's a major difference between the actual value and the estimated one. So what Euler's method does is it takes a linear approximation, uses a point on the linear approximation, but not exactly as far as 1.4. So in our case, it uses a 1.2. Here, it takes another linear approximation, similar to the first one, except more based on the graph. That way, you end up producing, if you take more linear approximations, something very similar to the graph in sort of shape and direction, although not directly. And this helps to estimate graphs where it goes on to infinity and such. So in our case, we're starting with a linear approximation that, in fact, we found in step A. And I'm not going to explain this because sometimes FRQs are connected, and so it's important not to erase your work and to show all of your work clearly so you can use it again in future parts of the FRQ. So we start off with this equation. Now, we're just doing a simple linear approximation with using the step size. So if we start out with a 1 and the step size is 0.2, the next step would be 1.2. And essentially what we're doing is just by plugging in into x. And one thing to notice is the thing inside the brackets is actually just the delta x. So this, when we plugged it in, is 0.2, and same will be applied if it's the equal step size. So when we do this, we end up with a value of 16.6. And this is the y value for when x equals 1.2. So we can just write it out here. Now, we need to take another linear approximation, as it says to use two steps of equal size. And so we're drawing a unique linear approximation by making another tangent line and using the x equals 1.2 values. So in this case, y equals the slope at x equals 1.2, which is 12, not 8. So be careful not to reuse it. And x is minus by 1.2 instead of 1. And it's added by the y value at x equals 1.2, which is 16.6. And from this, we can once again use the next step to approximate using the tangent line of at x equals 1.2 to approximate this. In this case, this is again 0.2 plus 16.6, and this is equal to an answer of 19. So for part D, it says to write a second-degree Taylor polynomial for f about x equals 1, which is the center, and to use this Taylor polynomial as a means to approximate f of 1.4. Now, first of all, we need to explain what Taylor series is. And it's essentially when the series has n equals 0 to infinity of f to the nth derivative of the center over n factorial times x minus the center to the power of n. Now, using this idea, we can sort of write out the second degree Taylor polynomial. So the first term, n equals 0, you can plug in 0 for everything. So when f is to the 0th derivative is just essentially f of 1, which is 15. And then since 0 factorial is 1, and x minus anything to the power of 0 is just 1, this thing is essentially equal to 15. And then you're adding it with the n equals 1 term. And another thing good to know is to use Taylor sort of notation. So in this case, we're estimating n equals 2, so that's why we're using 2. And don't confuse series with polynomials. It's a slightly different. Series essentially means writing out this, whereas polynomial is writing out the terms of this series. Now, n equals 1 is essentially the derivative at 1, which is, again, 8, as given on the table. So 8, and then divided by 1 factorial, which is just 1, and then x minus 1 to the power of 1 is just x minus 1. So that is our n equals 1 term. And then our second degree term, or squared, is our n equals 2 term. And essentially what we need to do is consider f to the second derivative of 1. And I told you at the start that you might need to use this at some point, and we do. So it gives the second derivative at 1, which is 20. And then we times it by x minus 1, which is the center, to the power of 2, or n. And then that's our second degree. And then we need to divide it by 2 factorial, so essentially you're timesing it by 10. And then it's good to simplify, so 15 plus x minus 1 plus 10 x minus 1 squared. Now, we're not done with the question yet. It says to use this Taylor polynomial to approximate f at 1.4. And so we can use this to approximate it by just plugging it in. So this is just some arithmetic. If you plug it in, you'll generate a value of approximately 19.8. And this is another way to approximate it using Taylor polynomials. Thank you for watching, and I hope you have a great day.